Continue on with our derivatives example. This time we have a capacitor. And so it says, let C denote the capacitance in farads of a capacitor. And it gives us a value of 25 microfarads. And we're given an expression for the voltage that involves E's and signs, you see there. And what's the determined expression for I of t? So, again, we set up our problem. We have our givens. We have our required and our solution. Again, we run into the problem of, unless we know more about the system, we don't know where to go next. We know from our previous thoughts, we know that current is the derivative of charge with respect to time. That doesn't help us get anywhere yet. Unless we know this other bit of information, by we can pull it apart using the chain rule, as we did before, which is we can split it into the derivative of charge with respect to voltage times the derivative of voltage with respect to time. We know we're going to be able to solve that, although a little bit complicated. But it turns out this dq dv is actually what capacitance is. Our amount of charge per voltage is our capacitance. So then I becomes a much more simple expression where it is simply C is equal to dV over dt. So given that key info, we can start with the voltage with respect to time. And one thing interesting about this is, what does this thing actually look like? Well, if we think about these two functions being multiplied together, we know the sine function just bounces between 0 and 1. So it's really, you can think of this as a sine function, but with the amplitude, instead of it being just a constant like we're used to, where it goes completely in between there, it's actually follows this function. So if we think about those two things independently, they look something like this. So not great artwork here, but yeah, if we think of this expression, it looks something like that, where as it gets close, as it goes out to infinity, it approaches 0, because it has a negative exponent there. Sine wave just bounces across through there. So what these look like when you put it together is a function that looks something like this. It looks something like this, where at the beginning you have the sine wave that had very stiff, very tall peaks, and then as it goes on, it kind of dampens down, so that as we go out to infinity, it's still bouncing up and down, but through a very small amount, just barely bouncing across the axis. Not necessarily something we have to know to be able to solve this, but interesting nonetheless. So again, we want to try to find the derivative of our voltage. I keep wanting to say velocity. This is voltage. And again, since we have two things multiplied together, we're going to have to use product rule. So I'll let that be my first expression, that be my second expression. So product rule, I'm going to actually skip an extra line here, sorry. Says that I take the first times the derivative of the second. And so again, when we do sine, we get this coefficient out front. It becomes cosine, and the inside stays the same. So that's first derivative second, plus, just because I ran out of space since I drew a picture, the second, which is sine of 5,000 pi t, times the derivative of the first, which is 20, times, I take that exponent to negative 500, and the expression in the e part stays the same. So then I could start to simplify those a little bit. So in simplifying that, I have 20 times 5,000. That is giving me 10 to the 5th pi. I still have that e to the 500th t, and I still have cosine of the thing there. For the second term, I have 20 times negative 500, so I end up with negative 10 to the 4th. The e to the 500, negative 500t, and I still have sine of the function there. So again, what would probably look better on this is to factor out some of the common factors. So I can pull out 10 to the fourth from each one of them and e to the negative 500t. So the first part ended up with 10 pi times the cosine of our function, of our expression, 5,000 pi t. And minus all that's left over here is the sine of the 5,000 pi t. So that's my expression for voltage. But remember, what I'm trying to get at is I, which is C times V prime of t. I'll just write it as V prime. So I of t is, we said our capacitance is 25.0 microfarads. So microfarads, if we remember, is times 10 to the minus 6 farads, which will help us. So if we take that times 10 to the fourth e to the negative 500, and then we've got our other expression, 10 pi, and so on. Then we can multiply these together and simplify things a little bit. 10 to the fourth times 10 to the minus 6 will just get us 10 to the minus 2. And so, yeah, we just end up with 0.25 e to the negative 500t times this quantity of 10 pi times the cosine of 5,000 pi t minus the sine of 5,000 pi t. Again, we could keep simplify that. We could use what we learned in sinusoids and actually reduce this into a single sinusoid with a phase shift and that sort of thing. Will probably look a little bit better. But this is enough to be able to get any answer we need to later. So we'll just leave it at that. So again, that's our answer. Our key points here are we need to know how to use capacitance to relate it to current. And then of course we use the product rule again, which is a little bit more complicated example.